Next presenter will be Erik Happi Stenman. So while Erik is walking up and also getting everything set up. Yes, so while Erik is setting everything up, I will introduce Erik. He's the CTO of Happi Hacking, helping companies with software projects. Erik is one of the one of the world's most experienced Erlang developers. He's been programming Erlang since '94. As a master student, as a doctoral student in the HiPE research group at Uppsala University. Also worked and was part of starting up, or was one of the first developers in Klarna also, in the famous CRED department. Welcome, Erik, to funcprogsweden.
Thank you.
Welcome, and the stage is yours.
Thanks. So I will talk about virtual machines for functional languages today. And I will start with a story from real life. So I worked at a small company. There were not 7,000 employees, there were 7 employees. And we had a service serving just a few customers. But in a few years, it grew to serving many, many customers. And then one very calm night, almost nothing was happening in the system because all our customers were basically in the same time zone, so not much happening in the night. But then suddenly one of the server nodes just disappeared. So what had happened was that this service was of course implemented in Erlang, and Erlang runs a number of schedulers, and one of them thought, well, this is such a calm night, so I'll just go to sleep, just as my son here in the picture. And since we had a machine with many schedulers and many cores, there were many schedulers, but several of them actually went to sleep because there were not much work to be done. And then there was one poor scheduler still up late at night working, and then it tried to do a built-in function in Erlang called term to binary, which takes an Erlang term and turns it into a binary representation that you can write to a log or send to the network or something like that. And it tried to do it on a 30 gig big term. So that, of course, took some time, and it was only one scheduler. And term to binary in Erlang at this time was not preemptive. I will get back to this in a while. So outside the Erlang system, there is actually another process that's called heart, that sends a heartbeat to the Erlang system and checking whether the system is live. And since there was only one scheduler running, and that scheduler was busy doing term to binary, there was no answer to the pings from heart. So then heart actually kills the system and hopes that a restart will set everything back to normal. So this is symbolized by my wife with the sword going for the kill here. So that got me more interested in actually understanding some of the deep down settings of the virtual machine of Erlang, and I started writing a book about the Beam system so that everyone coming after me now can hopefully more easily understand some of the deep down problems you can find. But today we're going to talk about two virtual machines solving two very different problems. So these different problems prompted some different language designs, and these languages in turn impacted the design of the virtual machine for the language. And we'll look a little bit into what these machines look like. So the first problem was making telephone exchanges. So this was in the early 80s at Ericsson. They realized that the majority of the development cost of a telephone exchange was actually in software. So the computer science lab at LMTEL at that time, it was Ericsson plus Telia together, set out to find out how do we want to develop software for telephone exchanges. So they saw that, well, telephone exchanges, they're always running. They have high throughput. They need to be reliable, and they need to be maintainable. So when you put a telephone exchange out in the wild, it will probably run for 20 or 30 years, or maybe even more. It turns out that these requirements came back when we started with internet and started doing web servers. So many web servers or any network service often have these requirements. So Erlang has, which is the language that was the solution to this problem, works also very well to make web services. The other problem is a little bit newer. It came with blockchains. So on blockchains after Ethereum came along, you wanted to write smart contracts. And smart contracts are neither smart nor contracts, but they are programs that you can run on the blockchain. So they're very different from an Erlang service, which is running forever. They run for a very short time. They need to be deterministic. So every time you run it on whatever hardware, wherever you run it, you need to get exactly the same result, giving the same input. And you want them to be reusable so that you can combine contracts. And they need to be easy to understand and verify, since they can handle a lot of money, real or imagined, or at least some tokens on the blockchain, which can represent money. And some banking services have similar problems, so could do with similar solutions. So as I said, the solution to the first problem was the Erlang language that was developed at the computer science lab. And the first thing that they realized in order to build a telephone exchange was that in a telephone exchange, they have at least two of everything in the hardware, because the hardware will break and then you want something else to take over. So you needed to be able to distribute your system and run it on more than one hardware at a time. And this led to the right concurrency model, a share nothing semantics with message passing. Also, they needed to be very easy to handle things that go wrong. And the error and exception handling in Erlang is quite robust and useful. Also, the philosophy when you write an Erlang program is very much like the Rail method that we heard, or as we say in the Erlang word, let it crash. So you usually write for the happy path and let the process crash if it goes wrong, and then you handle the unhappy path Also, there are a couple of things that are hard when you work with concurrency. So you want to make a couple of libraries where you really think about how to do these things. And we have things like gen servers and supervisors in the Erlang libraries. Erlang also became dynamically typed, and we'll talk a little bit on some advantages with that. There's also some disadvantages, of course. And it has symbolic and transparent data structures and an interactive shell. So it's very easy to log on to a running Erlang system and actually look at what's happening in that system and understand what's happening, because everything is symbolic and everything can be seen exactly what it is. It's not just numbers in memory. Well, in the end, it's just numbers in memory, but you have things on top of it to make it easy to understand. For the other problem, writing safe contracts for a blockchain, we came up with a new language called Sophia, which is statically typed. It has no concurrency, but it's possible to run several Sophia contracts in parallel with some thoughts on how to do that, as long as they are not touching the same path of the blockchain. It has very well-defined errors, and it's safe. So, for example, there's no wrapping of integers behind the scene, like Ethereum, for example, suffer from. It has a very close integration to the blockchain that it's using. It doesn't have any floats, because you don't want floats when you're working with currency. And it has well-defined serialization of all the data and the program, so that you can get the determinism also from that. So from the first problem and the solution Erlang, after a while we got to the virtual machine Beam. So there were a number of virtual machines for Erlang in the beginning. The first ones were just emulators written in Prolog, and then there was the Jam, which was very much like Warren's abstract machine for Prolog. But then came Beam in around 98 or something like that. And Beam is a garbage collecting, reduction counting, non-preemptive, directly threaded register virtual machine. And we will look a little bit at some of those things: the garbage collection, reduction counting, and that's about it we have time for today. So I said earlier that Erlang has schedulers. So the big thing with Erlang is, of course, that it's a concurrent programming language with many processes. And on the Erlang level, all these processes are preemptive. So as a programmer, you don't really have to worry about when a process is yielding and letting some other process run. But on the Beam level, in the machine level, it's actually non-preemptive. And it uses a thing called reduction counting. So reduction is a word that comes from Prolog. And in Prolog, Prolog is trying to reduce two terms until it can find an equality or a binding that makes two terms equal. And each part of that is a reduction. Erlang kept that word and uses reductions. It's not really clear what the reduction is, but at least every function call is one reduction. So every time you enter a function, the beam checks if you have used all the reductions that you got as a process. And if you're down to 0, then you let another process run for a while. A reduction should be something small, but as we saw with term to binary, turning a 30 gig structure into a binary representation is not really small. So, but that was quite a long time ago, and the team at Ericsson, with help from people on the outside, also have now managed to get almost all the built-in function in the Erlang runtime system to either be able to yield or both be able to yield and to count number of reductions comparable to the amount of work that they are doing. And since Erlang doesn't have any loops, the only thing you can do is to do function call and build loops by tail recursion or just ordinary recursion. Then any loop will also burn reductions by being function call. If a process wants to receive a message, then and there's no message in the mailbox that matches the message you're looking for, the process will also yield. So that's the basic of the Erlang scheduling, and you're running usually one scheduler per core or thread or pseudo core that you have in the system. So you can set this up as you want with as many schedulers or as few schedulers as you want. So if you're running several other programs on the same machine, you might want to reduce the number of schedulers that you're running in the Erlang system. So the concurrency model of Erlang is to have lightweight processes. A process has its own stack and heap. We'll look at that soon. And there's no shared memory. You can only communicate between processes with message passing, or actually through signals, and messages is a special type of signal. And there's no data that is shared, and there's also no updates. Since Erlang is a functional language, you cannot really update data. So a process cannot destroy data for another process. Erlang also has monitors and signals, so that one process can choose to monitor another process and get a signal if that process dies or killed for some reason, and can handle that. So from a high-level view, a process is just memory. It has a process control block which keeps track of, for example, the number of reductions that you have used and where in the code you're running the last function and so on. You have a stack with arguments to functions and the return address of functions. And you have a heap where you can store long-lived data. And the stack and the heap together is about 233 words when you start. And also there's a mailbox where other processes can add messages. So if we have two processes here with their memory, the stack and the heap, that are actually one memory area growing towards each other with free area in the middle. And then you have the inbox And we have process 1 here that want to send a message, hello, to the other process. And the other process is not really waiting for the message hello, it's waiting for the message 42, at least for 1 second or 1000 milliseconds. So when this process want to send the message, it has hello on its heap. It starts by copying it to a message buffer within its own memory area. So this it can do without disturbing any other process. And then it gives this message buffer to the other process and put it a pointer in the inbox of the other process. So this is in the general case. In some cases, and depending on your setting when you start a process, if the other process is running on the same scheduler and is not running at the time, the message can actually go directly to the heap. But in the usual case, it's just moved to the inbox. This process is not waiting for the message 42. So this receive, it will not match the hello. So it will then just keep track of the messages it has seen and waiting to hope to get the message 42. And if a new message comes in, it will just ignore the seen message box and look for new messages in the inbox. But after 1000 milliseconds, it will give up waiting for the message 42 and just receive any message. And in this case, then it will copy the message that it had in the inbox and put it on its own heap. So Erlang is dynamically but strongly typed. So you cannot do like in some language like JavaScript, add a string to an integer, or in C where everything is just data or pointers and you can basically try to do whatever you want with it. In Erlang, it's strongly typed, so if you try to add a number to a string, you get a runtime exception. But it's dynamically typed, so the compiler will not stop you from writing code that tries to add these kind of things. Of course, if it's really obvious, the compiler will warn you and say, well, this will never work because you're actually trying to add a constant string to a constant integer, and then you can have warning as errors turned on, and then this will not compile. But the nice thing with being dynamically typed is that you can actually do hot code loading. It's very hard in a statically typed language to type a program for the type that's going to be in the future. And with hot code loading, what you do is that you actually change the implementation, and you can, in that way, actually change the type of a function while the program is running. And the reason often to update a program is that you might have gotten some types wrong, and you want to fix this in some place. And this would make it very hard with hot code loading, and also with having static typing of only parts of the program. You usually want the whole program to be able to do static typing. It makes it also very easy to be able to move heaps and stack, or maybe it's not the dynamically typed, but since Erlang is dynamically typed, it also has everything tagged to be able to keep track of the types. And this makes it very easy to move around heaps and stacks, and also to get the transparency of data. So you can always look into the memory and see what type all the data on the heap is. And it's making the garbage collection easy also since everything is tagged. Erlang has a set number of types. There's no way to make any new types in Erlang. You can make abstract data types, but the built-in types is all you got. You could argue that under atom here, there is actually a subtype that is Boolean, which is the atoms true and false also, that are both Booleans and atoms. And all the types, all the values in Erlang are comparable, and they compare from left to right in this picture. So an integer is smaller than a binary, for example. So a string in Erlang is a bit special. It's one character per in a list per character in the string, needing 2 words on the heap, one for the character and one for the pointer to the next element in the list. So the string hello takes a number of words. This is in a 32-bit representation. In a 64-bit representation, it's obviously twice the size. I really like Erlang strings though, because you can do string concatenation in order 1, which is really hard in most languages, because Erlang strings are actually IO lists. So one time OTP, the people that making, or the organization unit that's making Erlang, decided to introduce line numbers in errors. So there's runtime errors in Erlang, and they introduced line numbers. So what could possibly go wrong? This is like perfect. It's like everything: ice cream, popcorn, bacon, brownie, and chocolate sauce. That's all you want. But it turned out that at this time we had a little loop in the program that worked by throwing an exception. So you could do a deep search and then throw an exception and not have to go back through the call stack. And just for the sake of it, the developer who wrote that also did a stack trace where it caught this exception so that it could write a logging message if something went wrong. So this happened 20,000 times per second in the system, and suddenly it started to trying to find the line number for all the stack traces in this call, and that turned out to be not so efficient. Erlang has a copying generation garbage collector and just 1 heap per process. So there's a nice thing you can do if you know that you're going to do a calculation and then don't need all the intermediate data. You can spawn a process with a large enough heap to do the full calculation, and then just let it die, and everything is reclaimed without needing to do a garbage collection. You get also a very small root set only in the stack of one process. So you get a sort of incremental garbage collection already from that. You get improved cache locality because each process has its own memory. And you can also then have the stack and heap grow toward each other, and you get the cheap test and fewer pointers. And when you do the garbage collection, you only need space for the data of one process, not for the whole system. So the extra footprint for a copying collector is smaller. On the other hand, message passing is expensive because then you need to copy the message that you're sending from one process heap to another process. And it can also use a bit more space because the stack and the heap always have this free space in between, And this is not shared between processes, but each process is using up a little bit of space. If you only had one heap, then you would have the same free space for all and reduce the fragmentation that way. So that were some highlights of the theme. So we'll take a quick look also at FATE, as it's called, the Fast Eternity Transaction Engine, which is a virtual machine built on top of Beam in order to run Sophia and smart contracts for the Eternity blockchain. So FATE has no memory limit. Instead, it's controlled by a gas price and the costs, which make it hard to try to use all the memory that you can. It has no concurrency. It's statically typed and has no floats. It has very well-defined errors and close integration to the blockchain. It's a stack-based machine, and it has a well-defined serialization. So very close to the Sophia language, also has basically the same properties, and it has Erlang's integers that can be of any size and don't wrap around, which has been a big problem for other languages. So the data types in FATE are integers, booleans, address, which is an address on the blockchain. And this blockchain also have contracts, oracles, oracle queries, channels, and all these are first-class objects, not only in the Sophia language, but also in the FATE virtual machine. It has strings and bytes, tuples, and lists, maps, and variant types. So you can also define your own types in the virtual machine. It has bits and also a type for types, so you can reason about the types in the machine. And the code is built of basic blocks, so there's no addresses or instruction addresses in the machine. It's only sequences of instructions within basic blocks. And the function has code, and code is a list of basic blocks, and the basic block is a list of instructions. So no way to jump to any place where you want in the code. You can only enter at the beginning of a basic block, and you can at the end of a basic block you can jump to different places. And there's no way to write code to memory. The code is loaded when a contract is started, and that's all that you have. The size of data is unspecified, so it's not like there's a 256-bit integer or anything like that. There's no word size. And the implementation can choose how to store the data. It's very well defined how you serialize the data, but what you do during runtime, we don't care about. So if we look at Solidity, which is a program language for Ethereum, a identity function contract might look like the one on top here. And then we have the Sophia contract, same function, taking an integer, returning an integer. Can of course be arbitrary sized in Sophia. So if we compile the Solidity identity function to the Ethereum virtual machine, the EVM, then we get this nice bytecode. So it's full of push and pop and calls and swaps and a lot of instructions. So the Ethereum virtual machine is very low level. It's sort of based off how a CPU works more than anything else. So one of the first thing we did when we started with Eternity was to port the EVM to Eternity to the AEVM. And then we can compile the Sophia contract to the AEVM. So it's basically the same machine, slightly different programming language, which makes for slightly smaller code. But it's the same virtual machine, so it's not much that you can do there. But this is the bytecode of the Fate machine. So it's actually a functional program even on the bytecode level of the virtual machine. Of course, the words function and init and so on has representation in byte, but you can actually have this text and parse it to directly into the machine. So compared to the EVM, Fate is safer. It's typed, have structured data, arbitrary sized integers. The virtual machine is typed. So the language Solidity is also typed, but the virtual machine is not typed. But this virtual machine is also typed. And it's more efficient. So the code is on general for the AVM. If you compile the same program to the AEVM, it's almost 10 times larger. You get lower gas cost and faster execution. So to recap, the Beam and the Erlang runtime system, that's the standard implementation of Erlang. There used to be some other ones. There's not that many that hangs around anymore, and everyone is using the Beam now. Each process has its own stack and heap, and there's the Beam is the virtual machine that executes the code. Scheduling is controlled by the reduction counting. Garbage collection local to a process. It's also generational and copying. We didn't talk about that, but I mentioned copying garbage collector. And Fate, the fast attorney transaction engine, a way to execute smart contracts, type safe, deterministic virtual machine. And the memory is only limited by the gas that you have. It has very compact bytecode. That was what I had to talk about.
I will hop up on stage here. Thank you very much, Erik. Thank you very much. I have one question immediately. Have you written more virtual machines? Have you looked at more virtual machines, or
I might have written more virtual
yeah,
machines.
it's very interesting problem. This is like the nitty-gritty part. You know, when I did my when I studied at university, we look at VHDL code and assembler, and the last code you showed in Faith, it really looked like assembler code, like jump, you go here, you go there, like really how like the processor works.
Yes.
Yeah.
In my book, which is free on GitHub.
Yeah.
So you can just there. I actually take you through writing a virtual machine first in Erlang and then in C for small arithmetic expressions, just to show you how easy it is to actually write a virtual machine. And I think I had some somewhere I have
that sounds very interesting
yes.
in a way.
So you can find it GitHub, Happi, the Beam book, and
yes,
there you can find some more virtual machines.
Yes, very interesting. I also have one more question. any other computer languages people should look into, other than the main languages? You mentioned Sophia.
So Sophia is a blockchain language.
Yeah,
So it's very specific if
Yeah.
you
Into blockchain.
if you need to use that blockchain,
Yeah.
you want to use that. Of course, there's Elixir, which is a language for Beam. Beam has other languages like Lua, and there's a Lisp for the Beam also. But yeah, I prefer the languages that you can run on the Beam.
So we understand. Also, do you use Erlang today, or are you forced to use other languages?
Both.
Both. Okay. Yes. Yes. Thank you very much. Let's see. No questions. This was a very interesting talk. Thank you very much, Erik, and thanks for coming and visiting us and sharing.
Right.
Thank you very much. With that, folks, that was like the 2 presentation tonight. Thank you very much for looking. We will be back again in like end of June with another funcprogsweden. And if you want to come and present, or know someone that should present, or have some work they should present, please get them to reach out to me, or please share their names, and I will try to spam them and get them on here. That's it for tonight. So thank you very much, everyone, and goodbye.